Hey guys, today we're going to learn about rotational kinetic energy, specifically for the case where you have a rolling object. Alright, now if we have something like, I don't know, a wheel or a whatever it is rolling along, it doesn't just, slide forwards like that or something, okay, like it would for a block sliding forward. It also rotates as it does this. And so for an object like this, we wouldn't just say it has 1/2 mv squared for its kinetic energy. We would also have to account for the fact that the object is in fact rotating. So this first kind of kinetic energy, the 1/2 mv squared that any moving object has, is called K translational. Or if you like, you could also call it linear kinetic energy. It's just energy from something that's moving. But if something is additionally rotating, it also has this other kind, 1/2 I omega squared, which is K rotational. So it ought to make sense to you then that something like a top would only have the rotational kinetic energy. Something like a sliding brick or block of ice or whatever would only have translational kinetic energy. But something like a wheel, which is moving forwards while it's also rotating, is going to have both of those kinds of kinetic energy. More importantly, we need to be able to relate these two quantities to each other. And the way that we're going to do that is just going back to this equation that we learned about earlier in the unit, V equals omega r. Which, if you recall, we use that mostly for like merry-go-round problems, like the angular velocity of the merry-go-round is this, a kid's standing here, how fast is he moving, and we would just multiply omega times r. Turns out we can do the same sort of thing for a wheel, only we'll do it backwards. If we replace omega with v over r, then we're going to be able to relate the two kinds of kinetic energy to each other. So what we're going to consider next is what does the total kinetic energy of a rolling object look like? Because if it's rolling, in addition to, meaning rotating, in addition to moving forwards, it has both kinds of kinetic energy. So what we're going to need to be able to do is write an expression, like a simplified expression, for the total kinetic energy that it has based on how fast the wheel is moving forwards. And the interesting thing, at least I think so, is that the total kinetic energy isn't always just one thing for any rolling object. More than anything else, it depends on the moment of inertia formula. And so here I've presented you with several different moments of inertia. And what we're going to do is plug in the moments of inertia and the conversion that we showed for going between omega and v, and come up with a simplified expression for each of these. Alright, so first I'm going to do let's say the cylindrical, the solid cylinder. So for the solid cylinder, let's see, we'll have, it says the moment of inertia is 1/2 mr squared. So that means that when I plug that in over here, into this formula for rotational kinetic energy, I'll have that. And if you recall, we said omega is v over r. So if I plug in for omega and square it, I'll have v squared over r squared. Alright, as you can see, or as you should be able to see now, several things are going to cancel out in that, well, I guess one thing is going to cancel out in that formula, and that's the r squared, which is really kind of interesting. What it means is the radius of the wheel or marble or whatever it is actually shouldn't matter. And for the most part it doesn't. If something is rolling down a really bumpy surface, then it might matter, because a really small object isn't going to be able to get over the bumps as easily. But as long as it's a reasonably smooth object, the radius really doesn't matter in terms of determining things like the speed of the object when it gets to the bottom. Okay, and then the expression then for the rotational kinetic energy simplifies to, well, 1/2 times 1/2 would be 1/4. M still there, V squared. And the linear kinetic energy, just bringing that down, is 1/2 mv squared as usual. All right, so what this shows you then is that if it's got 1/2 mv squared of kinetic energy, it's got 1/4 mv squared of rotational kinetic energy for a solid cylinder only. So the total kinetic energy simplifies to 3/4 mv squared. All right, I'll show you in brief the algebra for the others. I'm not going to talk them through the way I did this one, but you can follow the algebra and see how those go. Shown before you are the derivations for the cylindrical shell in red, the hollow sphere in blue, and the solid sphere in green. So as you can see, the expressions for the total kinetic energy come out differently for each of the various objects. All right, and obviously if we had some other sort of object besides these four, there'd be some other expression for it, but these are the most common ones that you're going to run into for this kind of a question, because these are the things that are most likely to be, say, rolling down a hill. Now, how do we use those in an actual example is what we're going to look at here. So in your notes packet, you should be able to find example 8. So pause the video and find that. And what it's describing here is a solid cylinder, gives you a radius, and it's rolling down an incline, and says how long the incline is and what the angle is. Well, all right, so there's our somewhat round object, 30-degree incline, that says 30, and it's going 1.5 meters. All right, now the purpose of a lot of this information is for you to be able to use conservation of energy in order to figure out the speed when it gets to the bottom. All right, the kind of energy that it starts with, you ought to remember, is gravitational potential energy. And the formula for that is mgh, which is what we need the length of the incline and the angle for, is to be able to determine the height through which it actually falls. Oops, switched colors by accident. All right. Now, the first question here that's being asked is, what's the moment of inertia of the cylinder? All right, that really all I'm looking for. You could plug in numbers and stuff. All I'm really looking for, though, is just you look up the formula. It says it's a solid cylinder. So if you went back earlier in the video or in your notes, you could look up that formula and determine that it's 1/2 mr squared. It's always going to be something that you can look up the formula for, and you need to look it up and actually use it throughout the course of the problem, because as we showed, the expression for the total kinetic energy when it gets to the bottom is going to be different when it reaches the bottom based on the moment of inertia. The energy that it has at the bottom is going to be distributed differently between translation and rotation, and so we have to know the moment of inertia formula that we're plugging in to get there. All right, now part B. Conservation of energy, determine the speed of the cylinder when it reaches the bottom. All right, well, you should remember that it starts with gravitational potential energy at the bottom, which is UG is our expression for it, so mgh. Okay, the gravitational potential energy is divided up when it reaches the bottom between the two kinds of kinetic energy. We've got K rotational and K translational. So 1/2 I omega squared and 1/2 mv squared. Now, as we showed moments ago, if we plug in the moment of inertia formula, the 1/2 mr squared, and we plug in v over r for omega, The r's cancel out. Still got that 1/2 mv squared there. All right, and so the total kinetic energy, combining those two things together, is 1/4 mv squared plus 1/2 mv squared for a grand total of 3/4 mv squared. All right, and that equals mgh. All right, so mgh equals 3/4 mv squared. All right, well, the factor of m is going to cancel. The mass never mattered, as it usually doesn't for these kinds of things. And so we can solve for v now and get that v is going to be the square root of 4/3 gh. All right, now for the sake of brevity, I'm not going to go through and get the numerical answers for these things because it doesn't really matter what the number is. In terms of you knowing how to get it, it's going to be based on trigonometry. Okay, so going way back, if we want to know the height, and what we have is this distance here and this angle, those are related by the sine function. And so sine of 30 would be the opposite side, that's the height that we want to know, over the hypotenuse, that's the length or the distance the ball rolls, and so the height would be d sine 30 in this case. Okay, so 1.5 times sine 30. Whatever, that's going to be a number. We could then plug in that number down here into this formula for the final speed that we got, and now we know how fast it's moving when it gets to the bottom of the incline. All right, so that's what we would do if I really cared about getting a number for the answer. The point here, of course, is what is the process, and so hopefully that is all ironed out by that. Now, I want to consider a few hypothetical questions here very briefly. How would our answers change if the cylinder had been more massive? As you can see from the work that we did down here, the mass cancels out. So actually, the mass of the cylinder is irrelevant. The speed when it gets to the bottom would have been identical. All right, how about the cylinder had a larger radius? Well, that canceled out right here. Radius doesn't matter. I mean, unless, we are taking into consideration things like a really bumpy track. But assuming that doesn't matter, radius is irrelevant. All right, for 3, if we'd used a hoop, that would matter. That would matter right where we plugged in for the moment of inertia. If you recall, the expression for the total kinetic energy for a hoop came out to, instead of 3/4 mv squared, it came out to just mv squared. And so if instead we had mv squared there equals mgh, the final speed would have been just root gh, which is a little bit slower. So in fact, it's going to be slower if you have an object with a larger moment of inertia. All right, final thought. If the incline had been frictionless so that the cylinder does not roll, what would have happened? If the cylinder doesn't roll, then we get rid of the entire rotational kinetic energy term. It only rolls if there's friction. So that's gone, and all this other junk in here is gone. So actually, the equation would have just turned into mgh equals just the 1/2 mv squared, which would give us our very familiar answer from last semester of the final speed at the bottom is root 2gh. So faster. So it actually will be faster in the event that friction doesn't make it roll, which is kind of an odd idea. All right, that should be enough for you to get through the homework. Let me know if you have any questions. Thanks very much.